Good morning, class. We are looking at Module 5, covering chapters 10, 11, and 12. Here's chapter 11. Goodness of fit and contingency tables. Number 1, goodness of fit test in multinomial experiments. Here are the observed frequencies from 4 categories, 5, 6, 8, and 13 at 0.05 significance level. Test the claim that the 4 categories are all equally likely. And here's the process we go through. State the null and alternative hypotheses. What is the expected frequency for each of the 4 categories? This is something new because we are looking at a new concept. What is the value of test statistic as before? Find the critical values, make a decision. Remember, test of hypothesis has 4 steps, and I am adding this because of the nature of this section. In short, multinomial, remember binomial has 2 outcomes. Multinomial has more than 2 outcomes. That's all. That's the concept, so you have a better understanding of that. So here's the definition. A goodness of fit test is used to test the hypothesis that an observed frequency distribution fits or conforms to some claimed distribution. Goodness of fit hypothesis tests are always right if the sum of these weighted squared deviations, chi-squared equals summation of O minus E. O stands for observed, E stands for expected. O minus E quantity squared over E is small. The observed frequencies are close to the expected frequencies, and there would be no reason to reject the claim that it came from the distribution. Only when the sum is large is the reason to question the distribution. Therefore, the chi-square goodness of fit test is always a right test. In other words, when this is small, you fail to reject the null hypothesis. So here's some of the formulas. Equal frequencies, if that's the assumption for the case of a multinomial. E, the expectation, the expected value is n over k. That means n, the total sum, so you would add up all those observations and you divide by how many. There are 1, 2, 3, 4 categories here. 4 categories here. So the other one is that, of course, E is n times P is the proportion for each category is given. If they happen to be the same, so be it. If not, proportions may be different. They don't have to be the same. So E is equal to n over k, where k is the number of categories and n is summation of O, or observations. In this example, it's 5 plus 6 plus 8 plus 13. That would be the numerator. Division by 4 because there are 4 categories, 4 observations, and each is supposed to be 8. That would be the expected. Okay. Why is that the expectation? Because if we assume they are equally likely, which means in essence 1 divided by 4, that means 0.25 or 25% as far as the proportion is concerned for each case. So you could add them up and multiply by 0.25, it gives you the same answer. Given it's a multinomial experiment where k is 4 categories, alpha is 0.05. We use a goodness of fit test. Each expected frequency, which is 8, does satisfy the requirement of being a value of at least 5. This value must be at least 5, because if expected count is less than 5, the result of chi-square test will not be accurate. So we are looking at the same question, and we are going to continue by working things out. The formulas: test statistic chi-squared is summation of O minus E quantity squared over E. Degrees of freedom is K, the number of categories minus 1. And E, the formula is N over K, or summation of O over K, and we have calculated it to be 8. Therefore, H0, P1 equals P2 equals P3 equals P4, because there are 4 categories. All the proportions are the same. That's the claim. Why is that? Equally likely. H1, at least one of the probabilities is different from the others, and it's a RTT, right tail test, always. So that's the first step. The second step is to calculate the test statistic. Again, it's a small data. We can do it by hand. Needless to say, you don't have to do this by hand. I want to show you the work. So according to this formula, observe minus E quantity squared over E. So for the first category is 5. So 5 minus 8 quantity squared divided by 8. The second one, 6 plus 6 minus 8 quantity squared divided by 8, and so forth. Now you can do 4 fractions with the denominator being 8, or just 1 fraction with the denominator being 8. And so when you do that, each one, 5 minus 8, 6 minus 8, 8 minus 8, and 13 minus 8, each one is being squared. Add them up, divide by 8 the expected value, and that gives you 4.750. That is the test statistic. Critical value comes from the choice of alpha and degrees of freedom. Alpha is 0.05, degrees of freedom is 4 categories minus 1 or 3. And so from the chi-squared table, on the left column, you locate number 3. And at the top here, alpha is 0.05. You need the area to the right. Area to the right is 0.05. It's a right tail test. And the result is 7.815. And if you put it into a graph, you see this is a chi-square distribution with critical value of 7.815, and the test statistic is way into the non-rejection region. The tail is the rejection region. Therefore, the decision is very simple. Do not reject H0, or fail to reject H0. Some people are very careful with that. You have to write fail to reject. Either way is fine. So if you're rejecting H0, let's go back to the very first step. You're rejecting H0. What are you rejecting? Equally likely, which is the claim. So the claim is you're not rejecting H0. You are not rejecting the claim. The claim becomes true. The claim is true. Now let's do the writing. There is sufficient evidence to support the claim that the 4 categories are equally likely. Now, couple of things. First and foremost, if by any chance you wanted to do this by a 2-tail test, then the 0.05 would be divided by 2. For the left side is 0.025. For the right side is the same thing. The area to the right for each one is calculated. And so the chi-squared of the left, when alpha is 0.975 with the degrees of freedom of 3 is 0.216, and chi-squared of the right, alpha is 0.0215, the area to the right is 9.38. And even in this case, look at the test statistic is in between. It's in non-rejection region. However, how do we do this? By hand. First of all, this is another one just to remind you of one of the calculators. There are many calculators online. You can find them under the module 0 of MOM. TI calculator, goodness of fit test, enter data, stat, edit, clear list, L1 and L2, observe value goes to L1, E goes to L2. So goodness of fit, stat test, chi-squared GOF, L1, L2, degrees of freedom is n minus 1. Let me show you just quickly what happens. In L1, you put the numbers 5, 6, 8, 13. And in L2, we have already calculated the observed value. And this is the observed value. By the way, it doesn't have to be the same for all. Because they are equally likely, that's why L2 is 8 for each one. Again, they don't have to be the same. They are the same because of this. After we enter those two, then chi-squared goodness of fit test observed is L1, expected is L2. It picks up those automatically. You really don't have to do anything if you always stick with L1 and L2. Degrees of freedom, you choose it, which becomes 3. You do the calculation. And here's the calculation. What do we get? First of all, we calculated the test statistic, and that's the same answer. Also, they do not give us the critical value. Instead, they give us the p-value, which is 0.19, way larger than 0.05. So p-value of 0.191 larger than alpha 0.05. Don't reject H0. We get the same result. All right. A professor asked 40 of his students to identify the tire they would select as a flat tire of a car carrying 4 students who missed the test and excuse. The following table summarizes the result. Use a 0.05 significance level to test the claim that all 4 tires have equal proportions of being claimed as flat. Here's the tire. L stands for the left, capital L. R is the right, lowercase. Capital R is rear. Capital F is front. So left front, LF, 11 said so. Right front, 15 said it got a flat. And left rear, 8. Right rear, 6. This is the observation. And if you add them up, 11 plus 15 plus 8 plus 6, there are 40 students. So we have the sample is 40. Now, E is n over k, summation of A O over k, the total of 40 divided by 4, or you can say n times p, it gives you 10. And when I say n times p, they are equally likely. There are 4 possibilities. Each one is 1 out of 4 or 0.25. So either way, number 10, which means each expected frequency 10 does satisfy the requirement of being a value of at least 5, because remember, we have to go with at least 5. So here's H0. The probability of each tire is the same. LF, we said left front, RF, the right front, LR, capital L, capital R, the left rear, and RR, the right rear. So 4 different locations for the tire, and that's the claim. Or you can say equals, and you can say equals 0.25 in this case. However, number of categories, 1 divided by that. If there are 10 categories, 1 divided by 10. Okay, 8 categories, 1 divided by 8. That would be the probability if they are equally likely. And H1, at least one of the proportions is not equal to 0.25, or P sub I is not equal to 0.25. It's a 2-tailed test, but we are going to go with right-tailed test. Remember, I told you that. Okay. And so, with that being the case, test statistic chi-squared is summation of observed minus E quantity squared over E. Again, you don't have to do it by hand, but it's small enough that we can do it. How? Very simple. 11 minus 10 quantity squared plus 15 minus 10 quantity squared plus 8 minus 10 quantity squared plus 6 divided by minus 10 quantity squared divided by E, which is 10. So it's really doable by hand. We get 46 over 10 or 4.6. So that's our test statistic. The critical value remains the same as the previous example because we have 4 categories and 4 minus 1 gives us 3 and chi-squared is 7.815. If we do the drawing, here's the tail. Chi-squared 7.815 is the critical value. Test statistic puts us way into the non-rejection region. Therefore, we don't reject H0. Remember, all of this calculation just results in this. Then you go back to the first step and reading to see where the claim is. The claim is in with H0, therefore the claim becomes true. And there's sufficient evidence to support the claim that all 4 tires have equal proportions of being claimed as flat. And if we were to go with the two-tail test, just as like the previous page, this number is in between the two, and you get to the same result, which is don't reject or fail to reject H0. So when 4 students identify the flat tire, it is not likely for all to select the same tire because there are 40 different students. They could easily make a mistake. So each one can pick something different if that's an excuse. Test of independence. Using a 0.05 significance level, test the claim that when the Titanic sank, whether someone survived or died is independent of whether that person is a man, woman, boy, or girl. I'm going to explain the concept of test of independence in a moment. But before that, let's look at this concept of expected frequency from the table. Here's the given table. So we are looking at one group. What is the group? The group of the people from Titanic. And we separate them into men, women, boys, and girls. And we are interested in categorical values, the variable surviving or not. So what it says here, according to that, 332 men survived and 1,360 died. For women, 318 survived, 104 died. Boys, girls. So this is the given. Now, the expected frequency says the row sum times the column sum over the grand total. So you add up this row, you put it here. You add up this row, you put it here. You add up this column, you put it here, and so forth. So if you add up these two numbers, 1692, these two numbers, 422, these two numbers, 64, these two numbers, 45. Now we're going to add up this way. And then this number is the grand total. So this is column-wise. Add these 4 numbers. Add these 4 numbers. And if you add these 2 or these 4, they must give you the same. And that is the total number of people that we are looking at in Titanic. So we have this many. Some are men, women, some are both, some are girls. And here's the numbers. Now, use the formula to find expected frequencies for the upper left-hand cell we find. Here's the thing. If I want to calculate this for this cell, 332, according to this, I'm going to, for this cell, the total number in the row is 706, in the column is 1692. I'm going to multiply these two numbers, and I'm going to divide it by the grand total. So these two numbers divided by grand total. So 537.36, that would be the expected value. What does it mean? If everything is independent, then we would expect this many men to survive. That's the idea. So using the same procedure, the table of expected values, and we do that for every element, every cell. But for 332, we showed the process. Again, you don't have to do it by hand, but it is important to see how it's done. More importantly, the meaning that I mentioned. So let me go over that. Interpretation. To interpret this result for this upper left-hand cell, although observed value says 332 men survived, we would have expected E equals 537.36 men to survive if survivability is independent of whether the person is a man, woman, boy, or girl. If they were independent, we would expect this number. There is a discrepancy between the observed value of 332 and the expected value of 537.36, and such discrepancies are key components of the test statistic, that is collective measure of the overall disagreement between the observed frequencies and the frequencies expected with independence between the row and column variables. Another one, if we want to do that, to interpret this result for the lower left-hand cell, we can say, if you look at this one, we're looking at this one. We can say that although the observed, which is equal to 1,360 men actually died, we would have expected E equals 1,154.64 men to die if survivability is independent of whether the person is a man, woman, boy, or girl. That would be the expectation, which is less than the actual number. That's the idea. Of course, note, summation of E in rows and columns are consistent, meaning if 332 and 1,360, they add up to this number. If you do the expected value row-wise, these two numbers, they add up to the same number. And these four numbers add up to this. Again, the only difference may be due to round-off error. So other than that, the addition of these four numbers is the same as addition of these four numbers. It should be, otherwise we've made a mistake. Or at the very least, it should be extremely close. Now, let's actually discuss the goodness of it. Contingency table. A contingency table or two-way frequency table is a table consisting of frequency counts of categorical data corresponding to two different variables. One variable is used to categorize rows, and a second variable is used to categorize columns. When data can be tabulated in table form in terms of frequencies, several types of hypotheses can be tested by using the chi-square test. One of them is test of independence of variables. There are various ways of approaching them. In a test of independence, we test the null hypothesis that in a contingency table, the row and column variables are independent. That is, there is no dependency between the row variable and the column variable. In other words, the test of independence of variable is used to determine whether two variables are independent of or related to each other when a single sample is selected. In the test of independence, observational units are collected at random from a population, and two categorical variables are observed for each unit. Tests of independence are always right-tail tests. If the sum of these weighted squared deviation, summation of O minus E quantity squared over E, just like multinomial, is small, the observed frequencies are close to the expected frequencies, and there would be no reason to reject the claim that it came from that distribution. Only when the sum is large is the reason to question the distribution. Therefore, the test of independence is always right-tail test. So that's the concept. We are dealing with one population, and we are looking at various groups. So as you're looking at this one, we're going to continue on that. The population of interest is the population that were in Titanic. All of those people in Titanic, one population. But we are looking at various groups of men, women, boys, girls, and the uh, fact whether they survived or not. We are checking the relationship, the dependency between the gender in essence and age in essence with survival. So requirement check. Let's assume random selection results are frequency counts and E must be larger than 5. As you can see, E in each case must be larger than 5. They are way larger than 5. So they all must be frequencies or numbers. So H0, whether a person survived is independent of whether the person is a man, woman, boy, or girl. That's one way to write it. Or you may say the row variable is independent of the column variable. That's the same thing. That's the claim. It is a two-tailed test. However, we make it a right-tailed test. Remember that. Surviving the Titanic and being a man, woman, or boy, or girl is dependent. That means the row variable is dependent or related to the column variable, and it's a right-tailed test. And so test statistic has the same formula. Degrees of freedom is the number of rows, R minus 1, times the number of columns minus 1. C stands for the columns. Okay, so let's discuss the test statistic. We've seen this before. Again, by hand can be done as far as the degrees of freedom, as I mentioned. See, we're going to look at it in a moment. But how do you calculate this? So this one is 332 minus 537.36. Quantity squared divided by 537.36. Plus the next one and the next one and the next one and the next one. And the last one would be plus 18 minus 30.709 quantity squared over 30.709. So here's the first one, here's the last one, and here's the answer. Degrees of freedom, okay, in order to find a critical value, you need degrees of freedom on alpha. Alpha is 0.05. Even if it's not given, that's your assumption. Degrees of freedom is row minus 1. We have 2 rows minus 1, so 1. Columns 1, 2, 3, 4 minus 1 is 3. So 1 times 3. So degrees of freedom is 3. Alpha is 0.05. Critical value 7.815 from the table. And if you look at this, here's the graph. Here's chi-squared 7.815, the critical value. And this number is way into the rejection region. So reject H0. So if you're rejecting H0, therefore you're rejecting the claim of independence. So the claim is false. There is not sufficient evidence to support the claim that when the Titanic sank, whether someone survived or died is independent of whether that person is a man, woman, boy, or a girl. Survival and gender are dependent. Now, if you go with the contingency table and you want to set this up, you use a matrix. So you access matrix by second and press x to the power of -1, edit, enter, stat, and then you do chi-square test. So here's what we do. We go to matrix A, and it's a 2x4 matrix. This is the matrix. And we put the observed value. Look at the very first entry is 332. The bottom is 1360. The next one is 318. The bottom one is 104. And the rest of them, 29, 35. And there's no room to show the fourth column. That's all you have to do. Matrix A is a 2x4. So now you go with the tests. You go with chi-square test. See, stat test, chi-square test. Observe is A. It chooses A, and the expected it chooses B. What about the expected? You don't have it. You don't have to have it. They will, in the process, calculate and give it to you. So when you don't have, the idea is that they will put that into the B matrix. So you calculate. Here's what you get. Take a look at what you got here. And if you go down, this is what you get. So first and foremost, this is the chi-squared value that was calculated here. Secondly, the P value, which is 0, definitely less than alpha of 0.05. So reject H0. By the way, this is coming from the table. It's very limited. Okay. Chi-square is larger than the highest value in the table. And you really want to stick with the technology. Reject H0. Notice it gives you, if you pick up the B matrix, look at the very first entry, 537.360. This is exactly what happens. It will calculate for you the B matrix, which is the expected one. You don't have to do this by hand, but you need to understand the concept. The whole module is basically done using a calculator. Test of homogeneity. Using the following table with a 0.05 significance level, test the effect of poster gender on survey responses by men. So men who agree, men who disagree, men, women. If the gender of interviewer is different, the answers are different about some topic that relates to men and women. That's the idea. Or even if it doesn't. Chi-square test of homogeneity, what is that? Also known as test of homogeneity of proportions, is a test of the claim that different populations or groups have the same proportions or distributions of a single categorical variable. The test of homogeneity of proportions is used to determine whether the proportions for a variable are equal when several samples are selected from different populations. It tests if the proportion of categories are the same across different groups. Test of homogeneity or right-tailed. If the sum of these weighted square deviations, summation of O minus E quantity squared over E is small, the observed frequencies are close to the expected frequencies, and there would be no reason to reject the claim that it came from the distribution. Only when the sum is large is the reason to question the distribution. Therefore, test of homogeneity is always a right-tail test. So we basically follow the same procedure as the test of independence. And so we add up these two numbers column-wise, these two numbers row-wise, these two numbers, and the grand total. So this is the grand total if you add these two numbers or these two numbers. So this is the total number of people being interviewed. So we can come up with the table of expected value in the same manner using the fact that E is the row sum times the column sum over the grand total for the sake of argument. If we want to look at this number 560, what do? The row is 868 total, the column is 800 total. Multiply these two numbers, divide by the grand total, okay? And you get this number 578.67. If they are independent, that would be the expected result. So men who agree, there are 560, but if they're independent, the expectation should be 578.67. Women, 308, but the expected value is 289.33. That's the idea. And so the requirement checks. Based on the distribution of the study, we will treat the subject as being randomly selected and randomly assigned to the different posters. Their results are expressed as frequency counts. They are numbers. The expected frequencies are all at least 5. If so, the count will be approximately normally distributed. And obviously, they are way larger than 5. That's the idea. They become approximately normally distributed, and the chi-square test works. So let's continue with that thoughts. So we are continuing with the same question. Again, we have the test statistic, the same formula. Degrees of freedom is r minus 1 times c minus 1. And this is the calculation that has taken place already. H0, the proportion of agree disagree responses are the same for the subjects interviewed by men and the subjects interviewed by women. P1 equals P2, P3, doesn't matter how many. Survey responses by men are independent of poster gender. So that's another way of writing. And in essence, test of homogeneity and the independent test, they follow the same procedure everywhere. The proportions are different. That's one way to write it. Or at least one proportion is different from the others. This is another way of writing it. There are 3 different ways of writing all of those. Or survey responses by men depend on poster gender, and it's a right tail test. Please take a look at all those 3 very carefully. They are 3 different ways of expressing H0 and H1. 3 different ways. You don't have to use all of them, but understand how they are expressed. Test statistic. So again, it's easy to calculate. For the first one, we say 560 minus 578.67 quantity squared divided by 578.67. The same thing for this one, the same thing for this one. Finally, and we are adding up, finally plus 92 minus 110.67 quantity squared divided by 110.67, and it gives us 6.52. Degrees of freedom, number of rows 2, number of columns 2. 2 minus 1 times 2 minus 1 makes it simply 1. Alpha is 0.05. So 2 minus 1, 2 minus 1. So in the left column, you look for number 1. Up here, you look for 0.05. The answer is 3.841. And if you go with the graph, you see that the chi-squared value of 3.841 is your critical value. However, the test statistic is way larger than that. It puts us way into the rejection region. So we reject H0, which means you reject independence. Which makes the claim false. And you're right. There is not sufficient evidence to support the claim that the proportion of agree-disagree responses are the same for the subjects interviewed by men and the subjects interviewed by women. There is sufficient evidence, or that's done. The second method to write it, there is sufficient evidence to reject the claim of equal proportion. That's done. The third method, survey responses by men depend on poster gender. And we are done. If by any chance we wanted to go with a two-tailed test, okay, chi-squared of the left, alpha is 0.975, degrees of freedom is 1. Okay, take a look at these 2 numbers. That's how you get them. We have these 2 numbers. And this is larger than the chi-squared of the right. It puts you in the right tail test anyway. So you end up with the same result. Test of homogeneity. Using the following table with a 0.05 significance level, test the association between people living in a city and becoming infected with a highly resistant bacteria. So we have people living location in the city or outside city. So we have 2 different populations, okay? And they are either infected or not infected by some sort of bacterial condition. And here's the numbers. And we use the same methodology, the chi-squared methodology. So first and foremost, step one, H0. Whether a person is infected is independent of whether a person lives in the city or outside the city. P1 equals P2, P3, P, and so forth. That is the claim. And whether a person, H1, whether a person is infected is dependent of whether a person lives in a city or outside the city. And we make it right tail test on purpose. So we need to calculate the expected value. Again, it can be done by technology, but I want to remind you of the formula. Test statistic chi-squared is summation of O minus E quantity squared over E. So I want to show you how it's done by hand in case it's really not too big of a deal. It's a small data. You add up this column. Okay, so these two numbers gives us 17,139. You add up this column, you add up this row, you add up this row. So, and this is the grand total. So remember, E is the row sum times column sum over grand total. So for this number that is highlighted, the row sum is 10,162. The column sum is 17,139, and the grand total is 42,048. Okay, those three, and we end up with this number. So the expected value is calculated for the first cell. You do the other. There are three more cells, and this one corresponds to the first one. This one corresponds to this one, this one. Just look at the same location. So look at this 4, look at this 4. Okay. Now, if we were to calculate the formula here, you would calculate one by one this number minus this number, quantity squared, and divided by this number. And it gives you this. I want you to just look at the very highlighted one, 4239 minus 4142.08, square the result, divided by this number, gives you this number. And you can do the rest. Because that's one way to do it. If you're using, for example, Excel, it makes it easy to do that calculation. So if you were to write it, you would rewrite it in this format. The last entry, this number, okay, minus this number squared divided by this number. And when you add them up, you add up those numbers, if you're again doing the Excel or those, and you get test statistic of 5.047424. Alpha is 0.05, degrees of freedom of 1 because you have two rows, 2 minus 1, 1, 2, and two columns. 2 minus 1, 2 minus 1. And chi-squared is 3.841, and we had that from the previous page. And if you go with the graph, you can see that chi-squared is 3.841, the critical value. Test statistic is larger than that. It puts you way into the rejection region. Therefore, you reject H0. As far as the technology is concerned, class, if you just run it by the technology, you get this one. Degrees of freedom is 1, alpha is 0.05, chi-squared test. Here's the critical value from the technology. Here's a test statistic from the technology, and it gives you the p-value, okay, which is less than alpha of 0.05, resulting in the same thing. So if you look at this, again, we have all of these numbers from technology here, as I mentioned, with, of course, more decimals. Get this number here, get this number here, and the p-value, as I mentioned. So reject H0, which means reject independence. And when you reject it, you reject what comes with it, which is the claim. The claim becomes false. There's not sufficient evidence to support the claim that whether a person is infected is independent of whether the person lives in the city or outside the city. And you're done. The second method of this part C, whether a person is infected is dependent of whether the person lives in the city or outside the city. And again, comparing the p-value from the technology, let's say 0.02 and change the 4 to 5, it's less than alpha of 0.05, and you're going to reject H0, resulting in the Same thing.